So today's lecture is on GPRS, and most of the slides that are in the slide pack are from a Nokia course that I wrote about 10 years ago or 9 years ago on GPRS. Now, what are we going to cover? We're going to cover an introduction to GPRS, look at GPRS architecture, the air interface of GPRS, how GPRS was able to make use of the existing GSM air interface, because GPRS is essentially a technology that works on top of GSM. And then we're going to see how GPRS does mobility management and session management. Now, in your last lecture on GSM, you have an idea of what the GSM architecture is and what the GSM air interface is like, and how is things like mobility management and session management performed in GSM. So basically, we're going to from that point we're going to see if we can extend the knowledge to the GPRS field. So the question is, what is GPRS? So essentially, what happens was GSM is a circuit switch technology. So in GSM, when you make a call, you allocated a time slot, and you hold that time slot for the entire duration of the call, and only when you finish the call, that time slot is released. So that for most of you, you will know that is the concept of circuit switching. Now, packet switching is a technology in which no resource is allocated to a communicating entity, but all of the resources that are available are shared amongst all of the users who want to transmit their packets. So the idea was, how could we offer packet switched technology on top of an existing GSM system? So as I said before, GSM allows circuit switch data transfer, in which you have a dedicated channel, and that dedicated channel is used for data transfer. It's set up just like in the old dial-up modems, where you dial in and you through your telephone network, and you hold on to that line, and while you hold on to that line, you do whatever data transaction that you want to do. It's very similar in GSM. Okay, you can also do a connection setup procedure, and then your time slot, and you allocated a time slot, and you hold on to that time slot in GSM, and then when you're finished, that time slot is released. And the charging in GSM is based on the amount of time that you hold on to the connection. So whether you transfer data or not, charging is purely based on the amount of time that you hold on to that particular time slot, which is a resource that the network allocates to you. Now, in GPRS, what we are trying to do is extend the existing GSM network, and we want to try and see how can we give packet switch service a connectionless packet switch service. Okay, so these two terms. Whenever you talk about circuit switching, you talk about a connection-oriented service, because a connection has to be established between the two transmitting entities before data transfer can take place, whereas in GPRS is called a connectionless. Most packet switching networks are referred to as connectionless because there is not a connection that is established between the end parties. Whatever resources that are available are shared by all of the entities that want to communicate. Okay, now the GPRS standard was standardized by an organization called ETSI, European Telecommunication Standards Institute, and then it's been now a well-established standard, and in some ways it's going out of use in some parts of the world, whereas in some other parts of the world it's just being rolled out. But all of the concepts that we come across in GPRS will eventually get used in 3G and subsequent networks. So all of the concepts that you learn here are very useful, because the same network elements such as SGSN and GGSN are reused in subsequent generations of mobile networks. So we talked about the fact that there's a need for packet switching services, and these packet switching data services have to coexist with existing circuit switches data. So the question is, how do we share the resources? Okay, so maybe one possibility is majority of the time slots could be reserved for circuit switching, but maybe a few of the time slots could be reserved for packet switching. Or maybe the way you change that, maybe at certain times of the day when there's a lot of circuit switch traffic, you allocate more of your time slot for circuit switching, and at other times of the day when the amount of circuit switch traffic has dropped and you have more packet switching services, packet switching requests from your users, you allocate more time slots for packet switching. So the question is, how can you share the existing GSM concept? Because remember, GPRS was essentially designed to be an add-on to GSM. So people didn't want to spend lots of money putting a new air interface and stuff like that. But so the idea was to maximize the existing GSM reuse of the existing GSM network. Now, one of the things is because packet switch GPRS was packet switch and it required different protocols, and there were slight modifications to the air interface so that it can work on top of GSM. The existing GSM terminals could not operate with GPRS. These were the terminals that were around at the time of standardization. So then they decided that new terminals were needed, and I think most of the terminals that are available nowadays, they're all GPRS enabled. So again, key point, the difference between circuit switching and packet switching. In circuit switching, circuit is established between the end parties, and that circuit is maintained for the entire duration of the call and only released at the end of the call. In packet switching, the concept of a circuit being established does not exist. It's a connectionless form of transfer. So essentially what happens is data is broken into small packets, and when resources become free, the packets are sent through the network, and we also see that packets from the same message, for the same message, different packets can take different routes through the network to get from the source to the destination. Whereas in circuit switching, even when you use data transfer and you're still breaking your information into packets, in circuit switching, all of the packets always flow on the same path because you're establishing a connection between the two endpoints. Okay, now how do we do that? So we already know from GSM that we have this concept of, we've already come across the concept of the BTS, the mobile station, the BSC, the MSC, and through the MSC you go out to the public switch telephone network, PSTN. These are existing elements in the GSM network. So the question was, how could we incorporate a GPRS network? And the way it was done was to, from the BSC, if there was a way that we could separate the circuit switch traffic and the packet switch traffic, so that the circuit switch traffic could go that way and the packet switch traffic could go this way, then we could siphon off the packet switch traffic and send it to something called the GPRS core network. And within the GPRS core network, we put in some new elements. The first element is called the SGSN, Serving GPRS Subscriber Node, which is this one here. And then the next node that we'll also introduce is called a GGSN, Gateway GPRS Subscriber Node, which is, GGSN is like a router that connects to the external network. So the external network could be the internet, it could be a corporate intranet, it could be a web service, anything that could run on packet switch services. So we find that users' information essentially travel on the same path from the mobile to over the air interface to the BTS, then to the BSC, and at the BSC packets are separate. The packets are separated and sent down to the packet switch network and out to the internet through the SGSN, through the GPRS backbone network, through the GGSN out and out to the external network. And the circuit switched information, which is primarily in the form of time slots, PCM time slots, are sent down to the MSC and out to the PSTN. So this is the basic idea behind the GPRS. Now the same thing happens when packets come from the external network. So when packets are coming from the external network, say you do a web browsing, and the results of the web browsing will be packets coming in the opposite direction. Packets in the opposite direction will also flow along the GGSN, SGSN, through the BSC, BTS, and back to the mobile. Now, with packet switching, we have to be very careful, because packet switching is essentially a very insecure form of transmission, and we'll talk about that a bit later. Now, I talked to you earlier about how to share your circuit switch and packet switch time slot. Consider the situation that we've got two TRIXs. Okay, now basically a TRIX in GSM is a device that can, so I use the word TRIX. TRIX is essentially a device that can handle 8 time slots. Okay, so imagine the situation where we've got two TRIXs at a particular base station site. So at most we've got 16 time slots. Usually some of these time slots are reserved for common channel signaling, but the remaining time slots are available for users. Now this diagram here represents how the time slots are used as a function of time. Okay, now there will be certain times of the day when almost all of the time slots are being used, like for example at this point in time here. Usually there's a lunch hour peak, so when everybody goes out to have their lunch, a lot of people make calls, and you might have a peak there, and so almost all the time slots are in that particular cell are being used. So, but it may vary. So after lunch you might have a dip, because everybody has to go back to doing some serious work, and they can't chat indefinitely on a phone. And so the number of time slots that are available, that are used by circuit switching, drops. So basically what we're saying is that there is this gap here, the area that I'm shading here, represents time slots that are not being used, because those are time, because we've got a maximum of 16. So the shaded area, the area that I've shaded just now, represents an area which can be used for GPRS. Okay, so GPRS packets could be sent in these time slots because they're not being used by circuit switch traffic. Again, it depends from operator to operator, but most operators make more money out of circuit switch traffic, so usually they prefer to give circuit switch traffic a high priority. So what are the sort of applications that we can use for GPRS? Now, when this technology came out initially, people were wondering, okay, what is GPRS going to be used for? But now we see that GPRS is being used considerably for quite a lot of things, because it's quite a reasonable way of providing packet switch services to mobile users. Okay, so this is all about mobile users. This is not for users at home. I'm sure very few users at home who have access to their cable network or dial-up modem will be using GPRS at home. But for when you're moving out, when you need bus information, train information, or airline information, when you want to locate restaurants, or you want weather information or security information, even taxis, I believe taxis that have cameras in them, so that when you go and sit inside a taxi, because a number of taxis have been bashed up, they've put these cameras inside taxis, and when you sit inside a taxi, it actually takes a photo of you and sends it back to the base station. And this is all, at present, a lot of it is being done on a GPRS network, and eventually those will move to a 3G network as well. So there's a whole bunch of applications that are being done on GPRS now. So anything where you've got bursty traffic, you would sort of use GPRS. Even some trains and trucks in which the engines have to be monitored and certain variables of the engines have to be reported back to a control station. You might have GPRS cards inside moving trains or moving buses, and data is collected of various things that are sensed, and that information is sent back to a control station, and again GPRS is used for that purpose as well. So why were operators or what are the advantages of GPRS to users and network operators? Well, for users, well, the main thing is that because you have this packet switched connectivity, you're always connected to a network. Okay, so for example, if you're the kind of person who wants to know as soon as you've got an email coming into your workplace, or if you need to know when a stock value has changed, or if you need to know all of these on the move, then GPRS provides that facility, because effectively what you're doing is that you're connected to a local area network. So as events happen in that local area network, that can cause your GPRS mobile to be notified of it. The other good thing about GPRS is the charging. Unlike in GSM, where you're charged for the amount of time that you hold on to that time slot, in GPRS, the amount of charging will mostly based on the amount of data you transfer. Okay, so when you're walking around and you're sort of connected to a packet switch network and you're not transmitting much information, you're not paying for that. Okay, so that provides certain advantages. And also GPRS compared to GSM can offer much higher transmission speeds. So that also has certain advantages from the point of view of a user. For operators, well, one of the main advantages that a lot of network operators chose to go with GPRS was they didn't have to put in new base stations, they didn't have to put new BTSs. All they had to do is minor modifications here and there. They obviously, in the BSCs, they had to put new cards in there, new cards that were able to separate the circuit switch traffic and the packet switch traffic. The MSC, they had to make some updates to the software that was on the MSC, and then they had to put on these new network elements like the SGSN, GGSN, and so forth. So for an operator, unlike the transition from GPRS to 3G, which involved putting out entirely new base stations because the air interface technology was completely different, the transition from GSM to GPRS was not too bad for an operator. The other thing that the operator had an advantage is that most of the time these empty time slots that are not being used and just sitting there, they were able to make use of this, make money of these empty time slots that were not being used by allowing people to transmit packet switch data in those time slots. And probably the third and most important one is that eventually all the operators were going to go to 3G. Okay, and in order to make the transition from GPRS to 3G, it's far easier to do the transition by going from GSM to GPRS to 3G than from going straight from GSM to 3G, because there was a lot of learning curve involved in GPRS, because GPRS was a packet switch network. It was essentially the first mobile packet switch network. So in terms of training people in your network who know about packet switching and how to find faults in packet switching network, how to do performance testing and so forth, GPRS provided an important transition point between GSM and 3G. So when they started doing the specs for GPRS, whenever you do come up with a new technology, you put certain requirements. So what are some of those important requirements? Well, the first important requirement that they specified was that GPRS had to make use of the existing GSM infrastructure. Okay, so as much as possible, use the existing GSM infrastructure. Maybe a little bit of modifications were allowed. Because obviously, if it was a technology that involved a lot of changes, maybe a lot of operators wouldn't have gone with it. The other thing that they also wanted was, they also wanted this ability to have more than one packet switched connection. So just as in your office, you might be reading your email and browsing, doing a number of different packet switch transactions at the same time, you want to be able to do the same thing on a mobile. Okay, so maybe a subscriber wants to, while chatting to somebody on the phone, might want to be web browsing, might be wanting to read the email and so forth. So it should be possible to support one or more packet switch connections simultaneous. Now, when they first came out, most of the phones were able to only do one, but now as time went on, their systems became more complicated, more sophisticated, and most of the systems can now handle 1 to 2 and even more packet switch PDP connections, as we'll talk about later. So these packet switch connections in the context of GPRS are referred to as PDP context activation. So whenever you do when you want to activate a data transfer, your mobile sends something called a PDP context activation, and when it does that PDP context activation, that is when it's allocated an IP address and all of the other things that you need to be able to communicate on a packet switch network. Now, they'd also specified in the standards that the system should be able to support different quality of service user subscriptions. Okay, when the systems came out initially, most of them only supported best effort, but as time went on, some of the other systems were able to support different quality of service. And the other one, the fourth requirement, was that when we go to 3G and then subsequently to 4G, there should be a lot of compatibility, so that you should be able to maximize, especially in the core network, all of the new elements that you're putting in the core network, like the SGSN and the GGSN, you should be able to reuse them when you go into 3G and 4G systems. Okay. Another requirement was that it should be able to support both point-to-point and point-to-multipoint data connections. What will be an example of a point-to-multipoint data connection? Maybe you're having a teleconferencing session, okay, where maybe 3 or 4 people are chatting to each other through their mobile phone. Okay, so there you have something called a point-to-multipoint. So whatever data is sent by one person has to be transmitted to all of the users that form part of that teleconference session. And the other thing is, because packet switching is insecure, you should provide security so that any security threat from a packet switch network can be, you can stop those security threats from affecting both the networks as well as the subscribers. Okay, so the next thing that we'll have a look at is the architecture of the GSM, the GPRS network. So we've already said that we have this idea of the BSS. The BSS is essentially from the GSM network, and the BSS is made up of the BTS and the BSC. So we're trying to maximize the reuse of whatever is inside this cloud here, and then we have to establish a new GPRS core network, because this is the network that handles the packet switching part of the network. The previous GSM network didn't have anything that handles packet switch network, so GPRS core network had to be established, and the GPRS core network could be connected to external networks, external packet networks like the internet and intranets, and it could also be connected to other value-added services like WAP and so forth. So let's go and have this is like a overview of what the architecture looks like. Let's go and look at it in a little bit more detail. So if we go in a little bit more detail, we see that the GPRS network has quite a lot of components here. Okay, so these components, the BTS and the BSC, these are the older components from the GSM era. And so we are introducing a whole bunch of new components here. The first one is the SGSN, which, as I said earlier, was serving GPRS subscriber node. The SGSN is like the main control unit of the packet switch network. It's like the MSC of the circuit switch network. So whatever the MSC had to perform in terms of circuit switch subscribers, the SGSN had to perform the same functions in the packet switch network. And the other thing that you also needed, that we've already talked about, is the GGSN. Okay, so the GGSN is a gateway to external mode. It's like a router. It's like a router that you have on a network that connects to an external network. So a GGSN is essentially a glorified router. It has to provide some extra functionalities that a standard router in a fixed line network does not perform. And also, whenever you have GGSN connecting to an external network, whether that is an intranet or an intranet, you need firewalls. So these firewalls are an important component in every packet switched network. Whenever any packet switch network connects to an external network, you have to place firewalls there so that you can protect the network from security attacks from external networks. So you've also got a whole lot of other components here. You have something called the DNS. Okay, so this from what you're studying in communication protocols or one of your earlier subjects that you would have done, you know that the DNS stands for domain name server. A domain name server translates between logical names and IP addresses. In the GPRS network, it performs a slightly different function. So the DNS that you have inside the GPRS network is slightly different to the DNS that you have in your existing packet switch network in the internet. You also have something called the border gateway, or BG, this one here. So the border gateway is a way of connecting GPRS backbone networks together. So you might have one GPRS network in Sydney, and you might have another GPRS network maybe in Singapore, and you might want to connect these two networks together, and that connection might be through the internet, it might be through lease lines, it could many different ways that you can implement that solution. But when you connect different GPRS networks together, you need something called a border gateway. And also, just as you have firewalls here, you will also need firewalls outside the border gateway. You have another unit called the legal interception gateway. So the legal interception gateway is a gateway that is used by, now this is a legal requirement. So every country, not every country, but in most countries now, all operators have to follow certain rules from the government. So if the government wants to intercept packets, if an agency like the Australian Security Agency wants to monitor packets that are transmitted by a specific user, okay, they can log into this LIG from whichever government agency it is, and they can specify, okay, this is a subscriber we want to monitor, and this legal interception gateway will track all the packets that are being transmitted by that particular user, and that that federal agency can then tap into all the conversations that a particular user is making. So this particular legal interception gateway came about because around this is around 2000, okay, and the world was changing at that point in time, and a lot of countries started to put these into their networks. In some countries, it's illegal to do that. I think in New Zealand it's still illegal for the government to intercept packets, but most of the other Western countries, and I think in most parts of the world now, legal interception gateways are accessible by government agencies that are responsible for national security. You also have something called the charging gateway here. Now, because GPRS does not charge based on the amount of time that you hold on to a time slot, it charges based on the amount of data you send. Okay, so you have to charge subscribers differently in a packet switch network. So the existing GSM network, which had the MSC and a billing center, cannot be used in this particular concept. So that's why the charging gateway was put in here, because it provided a means of charging for GPRS subscribers in a different way to the way they were charged in the GSM network. Okay, so those are the main building blocks of the GSM. So essentially, when you look at it, GPRS is like a packet switch network. Okay, these sort of components you will have in most packet switch. A packet switch network has the concept of routers, and it has the concept of DNS, and it could have other gateways that are used to connect different networks together. So it has that aspect, and it has also aspects to deal with mobility of users. Okay, so the SGSN is there to handle user mobility, traffic management, and so forth. And then you have the charging gateway there, because subscribers have to be charged based on the amount of data they transfer and so forth. So because of the different charging mechanism, we needed to put a gateway in there. And all of these have to talk to a network management system. So that's why you have the NMS there, and NMS manages all of these entities in a network. Okay, if you look in standard documents, you'll see a diagram like this. Not a very good diagram in my point of view, but I think the important things to realize is, all of the things that we talked about. You have your terminal equipment, mobile terminal, the UTRAN, or this could also be the BSS or the GRAN. It could be any of those. There's the A interface, the UU interface, and between the UTRAN and the SGSN, you have the IU interface, and this is SGSN. Okay, so SGSN is the unit that we talked about earlier, and you have the GGSN. Now these units, the SGSN and the GGSN, have to communicate with the MSC from the 2G network. They have to talk with the HLR. They also have to talk with the SMS gateway, and so forth. Okay, so these interfaces that are shown here are some of the common interfaces that you will come across. From the point of view of GPRS, probably the main ones. Let's see if I can get this to do it in a different color. Okay, so from the point of view of GPRS, you have the interface. The air interface in GPRS is called the interface, because it's similar to the air interface in GSM. Then from the BSC to the SGSN, you have something called the GB interface. Okay, and frame relay is the main transport technology that was used on the GB interface, although there were plans to move it to ATM later on. Then from the SGSN to the GGSN, you have something called the GN interface. And then from the GGSN out to the packet data networks, you have something called the GI interface. And then you also have this interface called the GA interface, because both the SGSN and the GGSN have to communicate with the charging functionality, and that is done through something called the GA interface. And then these units have to also interact with all of the older units from the GSM network. So the SGSN has to communicate with the MSC through the GS interface, the SGSN has to communicate with the HLR, because remember, all of the subscriber information is still in the HLR database. The HLR is still the same centralized database from which both the MSC VLR as well as the SGSN extract all of the important subscriber information. So the HLR has to not only communicate with the SGSN, it also has to communicate with the GGSN. Okay, so these are the mostly signaling channel. Common channel signaling number 7 is used on those interfaces, and they are used to extract subscriber information from the HLR. You also have the EIR. The EIR is the equipment identity register, and that's from GSM. That's primarily for terminal validation, and the same EIR connects to the SGSN, because remember, the SGSN has to deal with the packet switch subscriber. So just as the GSM network checks the terminals of GSM subscribers, the SGSN checks the terminals of GPRS subscribers. Okay, and then you also have the GP interface that goes on to. So these interfaces that are shown in blue here are the main interfaces, and you also have the other interfaces like GD. So there is a possibility for SMSs to be sent through the way in the GSM network, SMSs go through the E interface to the MSC, but there is also a possibility to send SMSs via the GPRS network. And they've actually, when they did some studies on this many years ago, they found out that it was more efficient to send SMSs through the GPRS network, because remember, when you send SMSs in the GSM network, you're taking up valuable SDCCH signaling channels, okay, and that can cause congestion in your network. Whereas when you send your SMSs through the SGSN, you're sending it on packet channels, okay. So packet channels are unused GSM time slots. So it's far more efficient to send your SMSs through the GPRS network rather than through the GSM network. So that's why you have this GD interface, because SMSs can go out to the subscriber on a packet switch network as well. So so you can see that the complexity of the network has got a little bit more here. And you have all of the, now one thing you'll notice about GPRS is all the GPRS interfaces that were defined by the HC, they all have the letter G. Okay, so that's an important thing. So as soon as you see, when you're looking at a diagram or a technical specification and you see an interface with the letter G, it should immediately hit you that that is a GSM, that's a GPRS interface. Okay, now eventually, in the previous slide, we saw how GSM and GPRS coexist, and all of the different interfaces. This diagram is a similar diagram that shows how the different networks coexist. This core here is referred to as the circuit switch core network, and the main elements in the circuit switch, and this is from GSM. So in the GSM core network, you had the MSC, the VLR, and so forth, and these also talked with other GSM network elements like the HLR and the EIR and so forth. And in the GSM network, you initially started off with, in the radio access network of the GSM network, you started off with a cloud here, which contained BTSs and BSCs. So in the GSM network, you had your traffic going from your mobile subscriber to the BTS on the UM interface, and from the BTS to the BSC on the ABIS interface, and then from the BSC to the MSC on the A interface. And usually there's a transcoder that is put in between these two, which is not shown in this diagram. So what I've shown here in yellow is what existed in the GSM network, and then what happened later on is they incorporated the GPRS network. So when they rolled out the GPRS network, they had to put a core network, and this blue cloud here represents the GPRS core network made up of SGSN, GGSN, on all of the other elements that we talked about, namely DNS, the legal interception gateway, the charging gateway, the border gateway. All of those form part of the packet switch core network. And then this GPRS packet core network had to integrate with the existing GSM network. So there was a GS interface to interconnect your SGSN with the MSC. You had your GR interface for connecting SGSN with the HLR, and you had the GB interface on which the packet switched traffic was separated at the BSC. So we had the packet switch traffic going this way and the circuit switch traffic going this way. So these were the, and then you also had the GA interface to the charging gateway and so forth. So these blue bits are bits that were added in when GPRS was rolled in. And next week, when we look at 3G, we will see how this network is then further evolved. And this is where the 3G core network is added. So here, when the 3G core network is added, we see that new base stations have to be added because 3G is going to be based on wideband CDMA. So you need new base stations, and you have a new type of BSC, which is called the radio network controller. But then when the 3G network is added, it will continue to use the existing GPRS core network for all of the packet switch traffic, and it will continue to use the existing GSM core network for the circuit switch traffic. And so you have these new interfaces called the RU interfaces that are going to be introduced, and we'll talk more about this red cloud next week, because that represents the next phase in the evolution from the GSM, which is the yellow bit here, to GPRS, which is the blue bit here, and then 3G, which is the red bit here. So all of these networks will coexist at the same time, because no operator is going to take out an entire GSM network, because GSM network has been very profitable for them, and it continues to be profitable for them. So they will continue to use the GSM networks, and as time goes on, slowly, the GSM network, all of the subscribers will be slowly shifted to the 3G network. And when that occurs, maybe a couple of years from now, then the GSM networks will be switched off. Okay. So this diagram is quite a good diagram because it shows how you evolve from GSM to GPRS to 3G. So we've talked about some of the elements in the GPRS networks. The first element that I'm going to look at is an element called SGSN. Okay, so as I said earlier, the SGSN is probably the most important and probably the most expensive element in the GPRS network, and it essentially performs the same function as MSC. And you have to have at least one of these SGSNs in your network for it to perform. So in fact, in Australia, when a lot of the operators like Optus first rolled out the GPRS network, they started off with one SGSN, and that one SGSN was looking after the entire country. But then as time went on and the traffic grew on the GPRS network, they rolled out SGSNs in different parts of the country. So you have to have at least one SGSN in your network, and SGSN performs a lot of important functions. Okay, now one of the things it has to do is eventually everything has to be transmitted as an IP packet on the GPRS core network, whereas in the BSS you might be using some other protocol. Like I said earlier, on the GB interface, which is the interface between the BSS and the SGSN, the initial specification specified that frame relay is going to be used there. So you needed a point at which frame relay frames had to be converted into a form that can be transmitted on the IP backbone. So that protocol conversion had to be done by the SGSN. Just as the MSC does with circuit switch subscribers, the GPRS was in charge of authenticating your packet switch subscribers. Because remember, a packet switch subscriber never needs to communicate with the MSC. All of their interactions is through the SGSN and out to the GGSN to the external network. So in terms of authentication, all of the authentication mechanisms that are there in GSM are now implemented in GPRS with slight modifications. And so the GPRS has to again go to the HLR and the authentication center and draw up all of that authentication vectors that are used for authenticating a GPRS subscriber. Mobility management. Okay, now we saw when you did GSM, there's this concept of a location area, and when subscribers move from one location area to another location area, the databases in the VLR have to be updated. Okay, because you want to be you only want to be paging within a location area. You don't want to be, when there's an incoming call to a subscriber, you don't want to be paging on every cell to find out where a specific subscriber is located. So in order to limit the amount of paging you do, you have something called mobility management, by which subscribers, when they move across certain boundaries called the location areas, then they do something called a location area update and inform the network in which location area they're currently located in. So in GPRS as well, you have to have the same mobility management, and GPRS uses a concept called routing areas. Okay, GSM uses location areas and GPRS uses routing areas. And again, whenever you have packets that have to be sent on the downlink to the mobile, then it has to know, okay, which particular area is a subscriber located in, so you can send the packet to the relevant GGSN and then down to the relevant SGSN. Okay, the SGSN has also got to do all of the signaling functions, just as the MSC does a lot of interaction with the NSS elements. The SGSN has to also perform these functions with the with the EIR, with the HLR, and so forth. The SGSN is also the collection point for charging information. So whenever packets go in and out of the SGSN, when packets come from the subscriber going to the external network, and packets from an external network go through the SGSN out to the subscriber, the SGSN keeps a track of the amount of data that is moving in and out per subscriber per PDP context activation. And at the end of the PDP context, when the PDP context is deactivated, then the SGSN informs the charging gateway, okay, this particular subscriber on this particular PDP context activation transmitted so many bytes of data and also received so many bytes of data, and then the charging gateway will then charge the subscriber based on the amount of data that was transmitted. It also collects statistics about subscribers, and again, all of the statistics go to the network management system, and the network management system keeps statistics about subscribers and also about what's happening in various routing areas, where is there blocking taking place, and so forth. The GGSN, as I said earlier, is like a router to an external network. So all of the functions that a router has to perform, it performs that. So whenever packets come in from an external network, when packets come in, those packets have to be routed to the corresponding mobile. So that function has to be done by the GGSN, and also reverse. packets that are originating from a mobile have to be sent to the correct external network. Okay, now the other thing that also happens in GGSN is that the GGSN collects charging data and traffic statistics. Now, the question, this is a question I've asked before. The question that I want to ask you now is, why is there a need for both the SGSN and the GGSN to collect charging data? Isn't that a duplication of tasks? So here, you can see the fourth point that we have here says that the SGSN has also got to collect charging data. So think about that question. Why is there a need for both SGSN and GGSN? Now, does anybody know the answer to that question? Anybody has a working experience in GPRS will probably know that. Why would you need to collect charging data both at the SGSN as well as the GGSN? Okay, now that's an important question. And if I were one of you, I would probably note it down, but you're not noting it down, so I'll carry on. Now, the GGSN is also responsible for allocating IP addresses. Okay, now, in a packet switch network, a mobile entity cannot communicate with an external network without an IP address. So that IP address has to be allocated by the GGSN. And there are two types of IP addresses that are allocated. One is called a dynamic IP address, and the other one is called a static IP address. Now, if it's a static IP address, and these are rarely used, you have the same IP address all of the time. Okay, now, in some cases, maybe in the case of maybe some important subscribers, maybe your corporate subscribers, you might give them static IP addresses. But usually, most of the time, you allocate dynamic IP addresses to subscribers. Now, you can also have, I'm expecting you, if you don't know the difference between a static IP address and a dynamic IP address, I'm expecting you to go and read about it, okay, because that is something that you would have done in any fundamental networks course. Now, a subscriber can also be allocated a public IP address and a private IP address. Okay, so you have two types of, just as you have static and dynamic IP address, you can also have public IP addresses and private IP addresses. Okay, so these addresses can either be allocated by the GGSN itself. So the GGSN could be allocated a pool of IP addresses, and from the pool of IP addresses, it allocates different IP addresses to different users. Or most of the time, in most packet core networks, there's already a DHCP or radius server. Okay, so the DHCP or radius server could be used by the GGSN to obtain IP addresses for the mobile subscribers. Okay, we talked about the border gateway. Whenever you have to connect two GPRS backbone networks, and the main reason you want to interconnect a number of GPRS backbone networks is to support roaming. Okay, so for example, the example that I gave earlier was you've got Optus that has got a GPRS network in Sydney or in Australia, and their partner, which is Singapore Tel, which also owns Optus, has a GPRS network in Singapore. Okay, now they might have some agreements by which any Optus subscriber goes to Singapore and wants to use GPRS, they can use the Singapore Telecom GPRS network for roaming purposes. Now in that case, because you're going to have a lot of roaming subscribers and a lot of roaming traffic, both Optus in Australia and Singapore Tel might establish their own network interconnecting these two through some backbone network, and a border gateway is then used to provide this tunnel between different operators' network. Okay, here's an example, which is the example that I talked to you about here. So this could be your home country. So maybe you're an Optus subscriber, and when you're in Optus network in Australia, you might be connecting through a specific GGSN to obtain your home services. And then when you go to a foreign country like Singapore, you might be connecting through the Singapore telecom network and going to the SGSN, which is in Singapore, and it comes, you go through a border gateway and maybe through a tunnel. This tunnel could be established, could be done through a number of different transmission medium. It could be, most likely it's going to be an underwater optic fiber cable through which your all of the packets from this country are flowing into this country, and a tunnel is established on that transmission link. It could also be a satellite link. And so when you are sitting in Singapore and browsing your GPRS on your GPRS mobile, you're browsing certain services that you have in your home network, then the packets will go through the SGSN in the visited network, through the border gateway there, through the border gateway here, to the GGSN in your home network, okay, and out to your home service. Okay, now this picture should answer that question that I asked you earlier, because I asked you a question earlier, why is there need to do charging at both SGSN as well as GGSN? Because of this situation, okay, when you are roaming in a foreign network, you might only be going through the GGSN in your home network, okay. So in that case, there's a need to, that's the reason why both the SGSN and the GGSN send charging information to the charging gateway, because then you can check the transactions that are taking place. Okay, now I talked about charging as well. Okay, now what happens in charging? Well, here's a mobile subscriber that's on a cellular network going through a BTS and BSC, and then down to an SGSN, and maybe the subscriber, some of the traffic is going through the GGSN to the local internet. So when you are, for example, when you are in Singapore and you're roaming, there are certain services that you might still have to go to your home network. Say maybe you're an Optus employee, and Optus has an intranet, and the Optus intranet only allows you to connect to it through an Optus router. Okay, in that case, your connection has to go through the SGSN in Singapore, through the border gateway, over this inter-PLMN network, to the GGSN in Optus, and through a specific GGSN that has been set up so that it can connect to the intranet, the Optus intranet. Whereas when you're in Singapore and you want to just browse the internet on another PDP context activation, you might not want to go, your packets to go all the way to Sydney for that. You could be using the local GGSN to browse the internet. So this is where this possibility exists, by which a subscriber, by specifying something called an access point, they can connect to different GGSNs in different parts of the world for different services. Now, because of that mechanism, there is a need for charging information to be generated both at the SGSN as well as the GGSN. And all of this charging information is then sent to the charging gateway, where the information is correlated and then sent to the billing system. So something called charging data records are generated by the SGSN and GGSN, and these charging data records are sent to the charging gateway using a protocol called GDP prime. So what does a charging gateway do? It collects all this information, it processes it, and then it passes it on to the billing system. Because at the end of the day, the billing system, this billing system that we have here is inherited from GSM. Okay, so it doesn't know anything about packet switching. It doesn't know how to process, the fact that this subscriber did so much amounts of packets at this point in time and so forth. So that's why the charging gateway has been put in between, because the charging gateway can then get the information from the SGSN and GGSN and put it together. Okay, I talked to you about the legal interception gateway or the lawful interception gateway. Now, in this diagram, you can see that any law enforcement authority, so this is a law enforcement authority. So in Australia, it is the, what is it called? ACO, yeah, that's the one, yeah. If they want to find out, if they want to monitor you, if they think that you have a strange background, maybe you have traveled to a certain part of the world too many times, and they say, okay, let's monitor this guy, let's monitor all the packets this person is sending, then that law enforcement authority can log into they have been given permission, so they can log into the legal interception gateway of any mobile operator. So whether you're on Optus or Vodafone or whichever operator you are currently on, all of the legal interception gateways are accessible by these law enforcement authorities, and these law enforcement authorities can specify, okay, this particular subscriber, they probably have the mobile number or the mobile records of that person. So they go into this legal interception gateway and they specify that every packet that this particular subscriber sends out, we want to monitor it. Okay, and then from this, the information goes to the SGSN and to the GGSN. Okay, remember it has to go to both because of this roaming possibility, and both of these SGSN and the GGSN then, whenever they see subscriber with that any packets with that particular IMSI, they are then, a copy of that packet is then sent to the legal interception gateway where it is stored, and then the law enforcement authorities can download them on a real-time basis. So this has been put in for security reasons in a mobile network. Okay, now there are other components. We basically talked about them, the DNS, the DHCP, and so radius server. I'm not going to spend too much time on these. DNS is exactly the same as a DNS in a packet switch network. It does conversion between a name and an IP address. Yeah, so the name that it converts is something called an access point name. Okay, so this is not your standard name that you put in your web browser. Every access point, every GGSN has a number of access points connecting to an external network. And when you want to connect to a specific access point, you put that in your PDP. When you do a PDP context activation, so when you want to connect to an external network, you do something called a PDP context activation, and in that PDP context activation, you specify something called an access point name. Now that access point name has to be converted to an IP address so that packets can be sent to that particular GGSN. That conversion between an access point name and an IP address is performed by the DNS. So the DNS in GPRS is not like the DNS in your conventional packet switch network. In the conventional packet switch network, it converts between what is referred to as a domain name and an IP address, whereas here in GPRS, the domain name server converts between an access point name and an IP address. Okay, now you may have a DHCP server. Now DHCP is exactly the same. This DHCP concept is exactly the same as a DHCP server that you have in a packet switch network. It has to provide important configuration information for a user. What are these information? The three main pieces of information are your IP address, the net mask, and the default gateway through which packets go out to an external network. So this is exactly the same, and all of these information have to be sent to your mobile host before they can start transmitting packets. Firewall, okay, again, firewall is exactly the same as a firewall in a packet switch network. So what does a firewall do? It prevents against attacks from external networks. So usually you place a firewall. This is your firewall that you place between a a secure network. So this is a secure network, and out here you have an insecure network. So a firewall is placed in that, and what happens is every packet that is going in or going out of this secure network has to be checked. So packets that are coming in are checked by a processor, and associated with this processor is an access policy, and this access policy is specified by the IT management in a company, and they specify, okay, what are the types of packets that we're going to allow through the network. So based on this access policy, packets that conform to the access policy are allowed, they go into the network. Packets that don't conform to the access policy, for example, if you receive a packet and the destination IP address is not within the range of IP address that the organization has, then those packets are discarded. Okay, that could be an example of an access policy. Similarly, packets that are leaving the network are also checked, okay, against some access policy, and if the packets that are leaving the network conform to the access policy, they are allowed to, they are permitted. Otherwise, they are restricted. Okay, let's go on to the GPRS air interface. So far we've had a look at an introduction to GPRS, and also we've had a look at the network architecture. Let's see how the GPRS air interface looks like. So essentially, when you look at the air interface, you're looking at the interface between the mobile and the network. So that's called the UM. In GSM, that was called the UM interface. There are a lot of functions that have to be performed on the interface. Any interface is usually the most complex part of any mobile network, because you have to do all the functions, all the way from the lowest layer, the physical layer, up to the network, the highest layer, the application layer. All of those functionalities have to be somehow implemented in the interface, but the most important ones are the lowest layer, the physical layer, the radio link layer, the LLC layer, the MAC layer. Those are the important functions that have to be performed by the interface. So modulation, demodulation, framing, error control, congestion control, media access control, all of these functions have to be performed at the interface. Now, just a quick revision about GSN, just in case you've forgotten it. I know you did it in your last lecture, which was about 3 or 4 weeks ago. So we know that in GSM we've got a 25 megahertz spectrum, and that spectrum is divided into 124 200 kilohertz carriers, and on each one of these 200 kilohertz bands, it's further subdivided into 8 time slot, and what each user is allocated is a time slot. So the time slot in G is referred to as a physical channel. Okay, again, very important in GSM to understand the difference between the physical channel and a logical channel. Very, very important concept, basic concept associated with GSM, understanding the difference between physical channel and logical channel. Now, in a GSM network, a physical channel, a time slot is a physical channel, because that is what is allocated to a user. Now, within a time slot, you can use it for many different purposes. So you can essentially, a time slot itself can be shared by many sources. Okay, so for example, in the case of signaling, on one time slot, many different types of signaling can be performed. And each of those represent a logical channel. So a logical channel implies partial use of a physical channel or partial use of a time slot by many different sources of information. So each physical channel contains a number of logical channels. Now you can also have within some of the channels in GSM are used for traffic purposes, and some of them are used for control purposes. Okay, so channels are usually divided into traffic channels and common control channels. The traffic channels are the ones that are allocated to users for making their calls, and the control channels are the ones that are used during the establishment of a call. All of the signaling takes place on the control channels. Even the sending of SMS in GSM is done on the control channels. So the traffic channel, which is only allocated after a call has been established and the called person picks up the call. So how does it work in the case of GSM? Well, in the other thing that can also happen in GSM is that you can have more than one tricks. Okay, so we talked about earlier that on each tricks you can have 8 time slots, and you can have more than one tricks in a cell. So you can, if you have more than one tricks, then you can have 8 or 16 or 24 time slots within a particular cell. Now these time slots can be used for one of 3 things. They can either be used for control signaling, and usually the first time slot in every tricks is usually reserved for control signaling, and then the time slots can be used for voice, which is your GSM, and whichever you can also reserve a portion of your time slots for data. So what is a packet data channel? Okay, so far we are aware of the term TCH. TCH represents the traffic channel that is allocated to a subscriber in GSM for voice transmission. A packet data channel is a channel that is allocated for data traffic. Okay, now this is the part at which we're going to go into a little bit more detail about how GPRS actually uses the existing GSM air interface. So you have traffic channels, TCH, and the unused capacity in any GSM network are used for packet data channels or PDCH. Now with the PDCH, a number of GPRS subscribers could be transmitting their data on one PDCH. Okay, now in the case of a GSM, one time, so how many users can be using one time slot? One. Okay, now you've all been told that most of the time only one user can use one time slot, but there's also that is using something called full rate. Okay, there's also something called half rate, where certain operators can implement a feature by which at one time slot can also be shared by 2 users. Okay, obviously that will result in a lowering of the quality of speech that you have, but in some situations it might be okay. So it is possible with something called half rate that that 2 GSM users could be transmitting their data on one time slot. Now in GPRS, we're going to see that it is possible for up to 12 subscribers to share one time slot. Okay, and we'll see how that is done shortly. Theoretically, it is possible for 12 users to share one time slot in the case of GPRS, because GPRS uses something called radio blocks. So the physical channel, okay, now again this comes back to understanding the difference between the term physical channels and logical channels. The PDCH represents a physical channel, a time slot. Now that physical channel is split up into a number of logical channels, and each one of those logical channels can be allocated to a user. Okay, now the packet data channels carry both the signaling that you need for GPRS as well as the data, the user data that has to be carried on a GPRS network. Okay, so there are many different types of signaling channels, just like we saw CCCH and BCCH and TCH and access grant channels and so forth in the case of GSM. You also have similar channels in the GPRS context. Okay, we've sort of covered most of the points on this slide here. The first one is that a GPRS uses whichever time slots or TCHs that are available in a cell that are not being used can be used for as PDCH. Okay, whatever time slot, we saw that diagram at the beginning where the green represented the number of time slots that are being used, and I shaded in a part and I said there is spare capacity, and that can be used for packet data transmission. So all of those shaded areas could be PDCHs, packet data channels. Now this allocation, the separation between, okay, which of your time slots is going to be used for GSM and which of the time slots are going to be used for GPRS can be done dynamically, okay, so based on the amount of traffic that's in the network, or you can do it on a static manner. You can say, okay, we're only going to allocate 2 time slots for GPRS and the rest of the time slots are for GSM. Okay, so it can either be done on a dynamic basis or on a static basis. Usually dynamic basis is a better basis because then you can change that border between GSM and GPRS. Okay, I want to go to the next slide, which has a good diagram here. Okay, so in terms, okay, so how does it work? Okay, now this is how GSM works, where you've got 8 time slots and you have the concept of frames. Okay, so a user gets allocated one particular time slot, another user gets another time slot, and so forth, and then it comes back. Then it is the same user who was allocated time slot 0 that transmit on time slot. Usually, most of the time slot 0 is reserved for signaling. Okay, so the one that is usually allocated to the user is TS1, starts with TS1 and all the way up to TS7. Now, so this is the idea behind the frame, is that all of these, the TS1 transmission in time slot 1 here and the user's transmission on the next frame, these all form something called a multi-frame. Now, in the case of GPRS, we have something called a radio block concept. So the radio block represents 4 consecutive time slots on the same time slot position. So what is allocated to a user is a radio block. So the basic allocation, so the minimum allocation that can be allocated to a subscriber is something called a radio block, which is 1 time slot position in 4 consecutive frames. Now remember, in GPRS you have a framing structure with 52 frames. Okay, so if you have a framing structure, a multi-frame with 52 frames, then if you're going to allocate 4 of those frame positions to one subscriber, then if you divide 52 by 4, you get 13. But some of the time slot positions are reserved for signaling. So that's how that number 12 that I talked to you about comes about. Okay, so I think the important point here is to understand the concept of a radio. The radio block is the basic unit that is allocated to a subscriber. So if you think of it, remember this is packet switching, okay? It is not circuit switching. So in packet switching, the network attempts to transmit your data, but packets can be delayed. In the case of speech, you can't delay real-time information, because then the whole idea of real-time data is that you've got to get that through. So here, as in GSM, a subscriber is allocated a time slot, and they have that time slot in every frame, in every multi-frame, except there are few that are used for signaling, but most of the time the subscriber has access to that time slot. But this is not the case in GPRS. In GPRS, every user is allocated only a radio block. That means they got in one time slot, one user transmits for frame 0, frame 1, frame 2, frame 3. Then the next user will come in. The next user will go on frame 4, frame 5, frame 6, frame 7. On the same time slot, the following user will then go on frame 8, frame 9, frame 10, frame 11. That will be the radio block for that particular user, and so forth. Okay, so the minimum block that a subscriber can be allocated is one radio block. A GPRS subscriber does not have exclusive use of one time slot. Okay, they only have use of a time slot for 4 frames, and then they have to give it up to another user to transmit their data. Now imagine that there was only one user. If there was only one GPRS user, in that case the user can take the first radio block, the second radio block, the third radio block, and fourth radio block, and so forth. So they can have the entire time slot effectively. But that is only in the case when there are no other users who want to transmit traffic. But imagine the case that you've got many users, then the minimum transmission resource that is allocated to a subscriber is one radio block. Okay, so that's a very important point that you have to understand in the operation of GPRS. Now, GPRS uses 52. It goes from 0 to 51. So a 52 multi-frame structure. GSM uses a 51 multi-frame structure. So the framing structure of GPRS is different to the framing structure that's used in GSM. Okay, so there are 52 frames. So again, if you divide 52 by 4, you get about 13. Okay, that's getting very close to the number 12 that I talked to you about earlier. Another way to look at it is this diagram here. This is quite a good diagram because it tells you how, imagine that this particular time slot you allocate for GPRS, so it has become a PDCH. Okay, it's a packet data channel. Okay, now the packet data channel goes up to 52 frames, so you've got 52 positions from the top to the bottom. Okay, now imagine that your radio blocks represent 4 consecutive time slot positions. Okay, and so that's one radio block. That's one radio block here. That's another radio block there. There's a third radio block here, and so forth. So you've got radio block 0, radio block 1, radio block 2, all the way up to radio block 11 at the bottom. Okay, so that's a total of 12 radio blocks. Now, some of the time slot positions, like this one here, and this one here, and this one here, and this one here, are reserved for signaling purposes. Okay, so you have something called packet traffic common control channel. So one time slot is taken away in that multi-frame, in that 51 multi-frame. One of those time slots is taken away for PTCH, and one has been kept idle. It has been specifically kept idle for Because sometimes when you write up standards, there might be certain situations that you might occur which you didn't plan for. So in which case you always leave something idle so that if there is a need, that particular idle time slot can be programmed to be used for a specific purpose. So you have 2 time slots positions out of the 52 structures that are reserved for common control channels, and you have 2 time slots that are being kept idle. Okay, and that's basically how the GPRS framing takes place. So it enables a maximum. Okay, remember the word is maximum. There's 2 aspects here. A maximum of 12 radio blocks can be transmitted on 1 time slot, which means theoretically a maximum of 12 subscribers can be transmitting packet switch data on 1 time slot. And the minimum amount that is allocated to any subscriber is this concept of radio block. But a subscriber in any network, more than 1 radio block can be allocated to a particular subscriber. Now, with these mechanisms, you can see that you can get a much higher data rate, because on every radio block, if you go back and look at the details, and this is a slide that I clipped earlier, you know that in each time slot, we can transmit 114 bits. Okay, if you look at the basic burst, GSM burst, you got 257-bit bursts and a trailing bit sequence in the middle. So we can transmit 114 bits in one particular burst in GSM. So now we're going to use this and try and see, and